Okay, so at the top of page 3, this problem is a little bit different in the sense that we're using the same standard format, but we're given a different function that we have to deal with. And what you need to understand is that here, this constant and this constant, as stated here, are like numbers, okay? So they are coefficients. So remember, with coefficients, when we're taking the derivative, which means you really need to think back, you do nothing with them. So if this was a 5 and I took the derivative, this would become negative 10e to the negative 2x. So because I don't know what the value is, when I end up taking the first and second derivatives, I'm just leaving these alone. They will stay there as c sub 1 and c sub 2. So what they want us to do again is verify, okay, that this is true. We need to verify. So what we're going to do is take the first derivative. So we know that y is equal to c sub 1 e to the negative 2x plus c sub 2 e to the 3x. So now when I take the first derivative, remember you're just leaving this alone. Okay, this is a coefficient. So if I just ignore this for 1 second, e to the negative 2x when I take the derivative would be negative 2e to the negative 2x. So that negative 2 is going to jump down in front. So negative 2 c sub 1, because whatever that number would be, I would multiply these together, e to the negative 2x, and this would be plus 3 c sub 2 e to the 3x. And then y double prime is equal to, again, you're doing the same thing. When you take the derivative of e to the negative 2x, it's negative 2e to the negative 2x, but now I need to multiply by another negative 2. So this would be 4 c sub 1 e to the negative 2x plus 9 c sub 2 e to the 3x. So now I have my derivatives, and I'm going to plug them in where they belong. So we have our second derivative here, which will go here. We have our first derivative here, which will go here. And we have our original function, which goes here, times 6. And what we want to verify is, does that equal 0? Okay? So let's plug these in. Second derivative. So this is going to be long, so make sure you leave yourself enough room. So you have 4 c sub 1 e to the negative 2x plus 9 c sub 2 e to the 3x minus, and because this is long, it's a quantity, so we're going to have to distribute. So I'm just going to put this in parentheses, negative 2 c sub 1 e to the negative 2x, and all I'm doing is copying my first derivative from over here, plus 3 c sub 2 e to the 3x, and then minus 6 times, and I will distribute, c sub 1 e to the negative 2x plus c sub 2 e to the 3x. So all I did was pure substitution, and what I want to know is, does this equal 0 once I simplify? So this is my question right here. Okay? All right. So what we're going to do is this will stay, distribute, distribute. So you have 4 c sub 1 e to the negative 2x plus. Let's distribute. So negative, negative becomes positive. Negative, positive becomes negative. Distributing a negative 6, this is minus 6 c sub 1 e to the negative 2x minus 6 c sub 2 e to the 3x, and again, does that equal 0? Okay, so let's take a look at what we have here. I've got all my terms with c sub 1, so let's look. I've got this one with an e to the negative 2x. I've got this one, and I've got this one. So 4 plus 2 is 6, minus 6 is 0. Okay, so these are now gone. Gone, gone, gone. And then I will use, I'm running out of colors, let's just use green again. So I've got this, this, and this. So 9 minus 3 is 6, minus 6 is 0. Verified. 0 is equal to 0. Check. Okay, so that is how you verify. I know you do have some of those problems in your homework, so please make sure you take a look. Let's start with separation of variables, which is 8.2. Okay, and I'm going to go through the steps here, and we will go through one problem, and I want you to try the second. Actually, I'll have to do the second problem with you also. Okay, so this is the procedure that we'll go through in solving differential equations for the first order. So this is if you have a first order or a first derivative, and this is the procedure. So the first thing that you want to do is separate the variables, okay, by rewriting the equation in the differential form, okay? And what that means is you're going to get all the y's on the left and the x's on the right. Okay, so this is what they have in their notation here. Your y's are on your left and your x's are on the right. Okay, then you will integrate both sides. Okay, so basically what you're going to do with this is just put an integral symbol on each side. Okay, so this is what it looks like. We have the integral of your y's is equal to the integral of your x. Okay. All right, and then it says if h, capital H of y, is any antiderivative of lowercase h of y, meaning the derivative of y prime dy is just y. You're going backwards, okay? And capital G of x is any antiderivative of lowercase g of x, then this is the equation that you'll get. So what you have is h of y, meaning you integrated with respect to y, and then you have g of x, capital G of x, because you integrated with respect to x. Now, on both sides, typically you would write plus c because this is a non-specific function. But typically what happens is when you're writing c, you're talking about any constant value that would go with either side. So this is typically, the plus c is typically put on the side with the x. So it's not incorrect to write plus c, but it is inconsistent to do so because the common mistake that's made is that people would subtract the c from here, and they get 0. But that's not always going to happen because if the c here is 3 and the c here is 9, you're not going to get 0. So what I'm saying is when you integrate, and it is a general equation, your plus c will go on the right side with x. Okay, so make sure you take care of that. And then typically you are going to be asked to solve the equation explicitly for y. And what that means is you're just going to write it as y equals. Okay, that's what that means. Okay, y is going to be equal to something, some equation. So you'll solve for y. All right, so what we're going to do is we're going to start with a, and I'm just going to highlight what goes together here. So in this case, this is solved implicitly, okay, which means you have dy dx. So we would have to use the separation of variables here. And I have my x here, and we're going to leave this coefficient with the x because that won't be difficult to integrate. And then you would have to move this over. Okay. So what we want to do is get this over here, meaning orange with orange, and get this over here. So we would multiply by dx, which means on the right-hand side I'm going to have 2x dx, okay? And then on the left I would have 1 over 1 plus y squared dy. Now if you look here, I hope you recognize this, but what this means is when you integrate, so I have all my orange together, and I have all my green together. Okay, you're going to integrate each side independently. Okay? So then what we have here is this is our inverse tangent of y. Okay, whoops. Okay, and typically we would write plus c, but remember the plus c will go on the right side. This is equal to the the integral of x is 1/2 x squared, and 2 times 1/2 cancels out, so this is just x squared plus c. Okay, so in this case, I have integrated both sides. Now, if we want to solve explicitly for y, which is what I want you to do and find a general solution, I want this in y equals form, we're going to multiply both sides by the tangent. So we are left with y is equal to the tangent of the quantity of x squared plus c, and that's your answer. It is solved explicitly for y, which is what step 3 states. Okay? Alright, so let's take a look at the second example on the bottom of this page. So first of all, this is written in terms of y prime. So whenever you have something like this, you want to rewrite it as dy dx so that you can use the separation of variables. Now, in this case, it doesn't matter where the negative goes. I typically do not move my negative. I'll just leave it. Any coefficients I'll just leave with x. So I want these two together, and I want these two together. Okay? So I'm going to multiply by dx and divide by y. So we have 1 over y dy is equal to negative x dx. Based on the second step, we want to integrate both sides. The integral of 1 over y dy, remember, you do not bring this to the top. This is the natural log of the absolute value of y is equal to negative 1/2 x squared plus c. So this right here is what we're looking for, but because we want to solve explicitly for y, that means we now need to get y by itself. So what we're going to do is, remember, exponentiate to get rid of the natural log. So now we're left with the absolute value of y is equal to, now here we essentially have e to the negative 1/2 x squared plus c. And what you need to remember is an old rule that when your base is the same, meaning if you had e squared times e to the x, this would be the same thing as e to the x plus 2. Okay, remember when your base is the same and you're multiplying, you add your exponents. So it goes either way. So because this is plus, what this really means is e to the negative 1/2 x squared times e to the c. If c is a number, that means this is just a constant value of some kind, because this would be 2.7 to whatever that constant value is. So what we can do is make this one big fat c and move it to the front. So typically what you're going to see is something like this. C e to the negative 1/2 x squared. Now what we have to consider here is the absolute value. If we do that, we're saying that this could be positive or negative. And when you're taking the absolute value, it would then be positive. So what we're saying is that y could be equal to either plus or minus ce to the negative 1/2 x squared. However, when you're taking the absolute value, this goes away, because c could be negative or c could be positive. So y is equal to ce to the negative 1/2 x squared. This is your explicit answer right here.